Hello everyone, it is so glad to be part of the Black Hat Arsenal community to have the presentation about our tool LibIHT, a cross-platform library for accessing the Intel hardware tracing features. And Intel hardware tracing features have been provided a long time ago with the Intel processors, and it is currently being widely used for performance analysis, for example, the kernel profiling. And for this presentation, we're trying to utilize those hardware tracing technique from a reverse engineering perspective and how our tool, LibIHT, accelerate this process. So before we actually dive in, we're gonna have a brief introduction about ourselves. So I'm Changyu Zhao, showing on the upper left of the photo. I'm currently the senior undergrad at the University of Wisconsin-Madison. And my partner Di Wu, showing on the upper right. He is currently an undergrad at Peking University. And our mentor, Guanchen Li, shown at the bottom of the page. He is currently the senior security researcher at Tencent Security Xuanwu Lab. Here's the agenda of this talk. At the beginning, we have the brief introduction of the program tracing from a reverse engineering perspective and a little bit background about the Intel hardware tracing features. Then we have enough knowledge to compare and contrast different tracing techniques and their limitation, and we will conclude that the LibIHT will be the best choice among of those. Then we have a more detailed introduction about LibIHT architecture and features, along with the user cases demonstrations. And the last one, we will talk more about the open source community of this project and the future development. So what is the program tracing? Program tracing, by the definition, is an art of understanding and reconstructing the execution behavior of a program. We have different trace levels based on different needs, like instruction level or function level and basic block tracing. As the diagram shown on the right, different white block are the basic block. It can be if branches or a loop. And the whole diagram can represent a function, and instruction is more detailed into different basic block about just CPU instructions. And we also have different trace techniques. The first one is dynamic binary instrumentation. And it usually by twisting the execution behavior of the binary by injecting some libraries or doing a just-in-time interpretation or compilation for the binary files. And the second one is the debugger based. I believe every software developer use this. The debugger attached to your process, and it can examine the registers, the context, and different variables, etc. And the next one is emulator-based tracing, because sometimes reverse engineers don't have the enough peripherals or the hardware environment for a target program. It can be a firmware or just a malicious program that can be properly sandboxed. So by emulating the CPU instructions along with that binary file, we can get the full control flow of that binary program. And the last one is the hardware assisted tracing, and we will talk more details in the next slide. So for Intel hardware tracing features, it actually provides three features. The first one is the last branch record. It stores the most recent branches of the from address and the destination address in those registers. And the registers are pre-printed in the Intel processors, so they have limited capacity. By knowledge from Intel manual, it varies from 16, 32, and to 64 at most. But accessing those registers are very low overhead. The next one is the extended one. For the LBR, is the branch trace store. It also have the same branch trace history as the LBR, and it logs the complete branch history in the memory rather than the registers. Therefore, it have a little bit higher overhead than LBR, but thanks to TLB, it's not that much overhead, but it can provide more comprehensive and customized approach for the branch history because you can customize your memory space to 1 gig or 2 gig or unlimited space if you can provide on your servers to record the whole branch history. And the last one is the Intel processor trace. It is currently being widely used for reverse engineering purposes. It has a very compact file format as the branch history result. It treats one branch jumps as the taken or not taken of a branch jump, and it records this 1-bit information in a very compact file. So it can provide very large program tracing with a little bit output. However, when you decode it, it's actually gonna rerun the program, and when it reaches the branch jumps, it will use the 1-bit information to determine if jump or not, and to recover this full control flow behavior of the program. So after all talk about this, what an ideal tracing technique we want for a reverse engineer? The first one is efficiency. We want our tracer to be fast, and as reverse engineers, you don't want to trace a small program for an hour to actually get this control flow. So the efficiency is the first, and actually the middle three is the quality of the tracing. The first one is the integrity. We don't want to miss any information when we do tracing, because as a reverse engineer, we already lost many information during the compilation of that program. So we want to get the most detailed execution flow of that program to help us do reverse engineering. And the next one is transparency. We don't want our tracer to be detected or affecting the normal execution flow of the binary file. This usually apply for the malware analysis because the malware will detect if you're gonna attach a debugger or not, or twisting their memory layout. So if they detect this suspicious activity from the user, they will not execute properly. It can be act like a benign process or even just stop executing. The next one is stability. We don't want our tracer to crash when we're trying to trace for a large program. We want it to be stable and trace whatever we want and to gather information we need. The last one is the usability. It is kind of the vague quality of the tracing techniques because it basically evaluates how many tools being integrated and what does this tracing technique provide user-friendly APIs, or how easy to use this tracing technique. So here comes the compare and contrast of different tracing techniques being introduced earlier and their limitations. So the first one is dynamic binary instrumentation. Here we have example of Intel pin, Dynamo RIO, FRIDA. For efficiency, because it is doing binary instrumentation. So at every instruction being executed, it have to log or record the current status of the execution behavior of the program. So the efficiency is very low. So there's a cross there. And the integrity, we have the very basic standard for the tracer. So it's a check mark there. The transparency, the dynamic binary instrumentation actually twists the binary very severely. The Intel pin, for example, it will do the just-in-time compilation of that binary program. And for FRIDA, it actually injects multiple other libraries that assist it for the tracing. So it's manipulating the memory layout or interfering the original control flow of that program. And the next one is stability. It's also a cross because FRIDA, for example, it can't actually trace a very large program because of the internal of that technique by injecting different libraries to the binary. And the next one is usability. They're the most popular tracing technique being used for reverse engineers. So the usability definitely a check mark there. The next one is debugger. And here we have the example of GDB or Win debugger. The efficiency, it actually depends on what granularity you want to trace. But ultimately, at every granularity, for example, the basic block, you have to pause and log the status along with your tracing. So the efficiency is low. The next one is the integrity. The debugger can have the accurate and complete trace result from the program. That's definitely a check mark. The next one is transparency. The debuggers actually use some special system calls to actually attach to the target process. So the malware actually can detect if you're trying to using those system calls to attach to them. So the transparency is not quite good, but it is very stable because it can use across multiple platforms, and no matter how large your program is, the debugger always works because that's how they've been developed and debugged. The next one is emulator-based tracing, usually QEMU and Unicorn engine. The efficiency is very slow because we need to emulate different instructions for the program. The integrity is good because we emulate every instructions, so we know what the control flow is based on the instruction information. The next one is transparency. Usually those emulator kind of act as the operating system. So the target process won't actually sensing there's tracing along with them, just act they are running at the operating system. And so we have full transparency for those process. And next one is stability. The QEMU can execute any large program and even the operating system, so the stability is very good. But usability, we have a question mark because QEMU actually need to configure a lot of stuff before you actually start tracing. And QEMU not cross-platform, so on Windows, you don't have this kind of emulator-based tracing technique used. And the last one, the hardware tracing techniques. We have all the benefit of the emulator-based tracing, but only left the usability as a question mark. So that's actually the main problem we want to resolve for LibIHT. So here comes to LibIHT, the Intel hardware tracing libraries. We bridge the hardware and user needs by providing user-friendly APIs in the user space, and we simplify the hardware tracing redundancies by adding a layer of abstraction in the kernel space to avoid the complex configuration of the hardware tracing. And the last one, efficient low overhead solution for large program tracing. So here's the introduction of the LibIHT about the architecture. Here you can see the LibIHT being divided into two parts. The first one at the top is LibIHT user-lib. It acts as a user component for communicating with the user space processors. You can have a monitor process to monitor different target processes. The target processes also can trace itself depending on the user need. And currently, the user library is the wrapper for the I/O control API exposed by the kernel components. So the user library then communicates with the kernel component for more detailed information about the hardware tracing results and the configuration about the hardware tracing. So the kernel components add another layer of abstraction for the CPU that avoid the user to set up the complex configuration for the hardware tracing features. And it provides a control for different target processors and actually monitor every process running on that operating system. The benefit of this architecture is because by dividing into two components, these two components can do their different job based on their duty. The next is the LibIHT features. We have efficient hardware-assisted tracing that internally provided by the Intel CPU. And we can do selective tracing for specific code regions with very fine-grained control. And there's also a feature for the Intel CPU. Next, we have advanced analysis capabilities by providing a complete trace information for control flow reconstruction. And this provides for more detailed analysis capability for later reverse engineers or also for performance analysis. And the last one is the user-friendly approach of this tool. It provides user-friendly APIs about enable or disable or even collecting and analysis of the tracing result. And it is cross-platform, so both Linux and Windows can be supported if they're running on the same hardware. So here comes the use cases and demonstrations. Here's a demo on the LBR and on the Linux platform. So first we insert our kernel module to the kernel. We will take a brief look at the source code. It is very simple. In the main function here, the function 1 simulates the critical logic. And you can see the enable and disable is very convenient by just in one API. Here, function 1 and function 2 is recursive calling each other to make a very complex branching or calling behavior of that program. So now we are trying to run the program with 10 recursive calls. Here we have the results. You can see those function pointers and the tracing results. They're actually the real branch jumps and the calling of the different functions. If we increase the recursive call to 11, we can see the LBR TOS is the top of the stack is increased by 2 because we have one more calls between these two functions. So this concludes Linux LBR demonstration. Here is the BTS demonstration running on the Windows platform. So the logic is basically the same, and two functions recursive calling each other. We will just see the results here. For BTS, you can see there's very long log of the full execution flow of that program. And this is intended because BTS allow you to customize the memory space of your tracing. So the same thing here. If we extend our recursive call to 11, we will see 2 or 3 more jumps of that tracing result. Yeah, this concludes the BTS demonstration on Windows platform. So here we have a user tool integration, the GDB plugin for the LibIHT. And it shows how powerful that LibIHT can be used even when you're debugging a program. If you want to examine the execution behavior in a function or in a small amount of memory region. So we use GDB to launch our program. We first source our plugin for LibIHT. Here's the source code, and it's also simple, just two functions cross-referencing each other. We set a breakpoint at entry of function 1, and at main, when we about to execute function 1, at the end of main, they return. So now we run the program. We hit first breakpoint. As you can see, we are just 2 more instructions for the calling. Now we enable the LBR. If we dump LBR now, because the program is not being run, so it just get nothing. Now we hit the beginning of the function 1. Now we dump out the LBR. By ignoring those kernel trampoline, we just start from looking at the third entry. We can see there's a calling, and the destination is the beginning of the function 1. So now we complete one recursive call. Here you can see there are also some kernel trampoline being involved. We just ignore it. And here we see in function 1, we called function 2. The destination is function 2. And in function 2, we call back to function 1. So now we disable our breakpoint at the function 1 with execution to the end of the program. Now we dump out the LBR about the latest branches being taken. Here we can see the functions are actually returning from this recursive call. Here's the return in function 1, and then there will be a return for function 2. Yeah, so after they finished up, the recursive call return, and now we disable the LBR. We execution to the end, and now we quit the GDB. This concludes the LibIHT demo on the GDB. So what's next about LibIHT? We are considering to implementing more tracing features. The architectural LBR is the latest support for the LBR feature, and Intel CET stand for Control Flow Enhancement. Those two new features can definitely provide more detailed and more powerful tracing by utilizing the Intel hardware chips. And what's more, we can have a better and more powerful user space tool integration. As already shown in the GDB, we can integrate to some other reverse engineering tools like the decompilers, the Ghidra, or the IDA as a plugin. By dumping out the execution flow we highlight in the basic block of the different decompilers. And the last one is the most important one, the community-driven feature requests and improvements. So come and join the LibIHT community. You are more than welcome to. And here's the GitHub link for LibIHT. And this concludes our talk. Thank you.